Okay, we're going to look at another indefinite integral problem here. So when I look at this one, I notice that I have this product of functions, and I'm trying to think about how this fits into the basic antiderivative rules I know. So I have some rules for integrating powers, x to the fifth or something like that. I could integrate that. I know that I can split up a sum into separate integrals. I know I can pull constants out front. So if all I had to integrate was just the 4x squared plus 1 without the fifth power and without the x, this would be a pretty easy problem. I could just do that pretty directly using those basic rules. If all I had to integrate was just x and not all this other stuff, that would also be a pretty easy problem. I could just use basic antiderivative rules. But the issue is that I have a product of functions here, and I also have a function inside another function. If this was a smaller exponent, I might think about just multiplying this all out and having a polynomial and just integrate each term separately. But for a fifth power, that's pretty hard. Even if you use binomial theorem to help you, there's a lot of terms there. This would have 6 terms, and I'd have coefficients like 4 to the fifth power would be one of the coefficients. So it's kind of a mess to do all of that. So I might think through, that is a possible way to do this problem, but I might think through whether there's another way to do this problem. And for this class, really, we've learned 2 ways to do antiderivatives, and that's all we will learn. One is basic antiderivative rules or do some algebra so that you could use basic antiderivative rules. So that is an option here, maybe not the easiest way. The other way that we've talked about is U-substitution. So when you have a function inside another function, sometimes U-substitution helps. So I would notice here that I have a function inside another function, and I would think through whether U-substitution would work. So how do you know whether it would work or not? You start by letting U equal the function that's inside something else. So in this case, that would be 4x squared plus 1. Just because I write that down doesn't mean it's actually going to work. I have to find the differential, the du. So I differentiate this with respect to x. So derivative of this will be 8x, and then I have the dx. Differential derivative of 1 is 0, 8x dx. And so at this step is when you can tell whether your U-substitution is going to work or not. You have to be able to match up all the variable parts of the function that you're integrating with the variables that you have here. You can deal with constants by multiplying or dividing both sides, but variable parts are what you need. So I'm looking at this original integral. I know that I need to have 4x squared plus 1 to the fifth power here, so I can handle the 4x squared plus 1 with this and think about that as u to the fifth. I'm going to go ahead and circle this and this. And then I also need to be able to handle the x dx. So this part right here in my du helps me decide whether this U-substitution is going to work or not. I do have x dx here and x dx here. I don't have an 8 in the original integral, so I do have to deal with this 8. We've been dealing with those constants in the same way in several different examples. You can divide through by a constant, not a variable, but a constant. And so as long as all of your variable parts match up, in this case they're kind of separated here, but those are still times each other. They're just written apart from each other instead of right next to each other. But as long as I've accounted for all the variable parts of the function with my u and my du, again with perhaps a constant that you have moved around, then your U-substitution will work. All right, so let's go ahead and do the substitution. So in place of the x dx that I have boxes around here, I'm going to put in 1/8 du. I can put the 1/8 du any place in here really, but I a lot of times will pull that constant out front and put the differential at the end. So I did not substitute 1/8 in place of x and du in place of dx. In place of both of these together as a unit, I substituted in the 1/8 du and just went ahead and pulled the 1/8 out front. All right, and then in place of the 4x squared plus 1 that I've circled here, I'm going to put in u, and don't forget that that's to the fifth power here. All right, so this is one I do have basic antiderivative rules that I can use. The 1/8 out front is going to just come along out front, and then antiderivative of u to the fifth power, so that's where we add 1 to the exponent and have 1 over that coefficient out front, so 1/6 u to the 6th. And this is the step where I have a plus c. And then one more step to finish. I need to substitute back in place of my u. So I'll have this 4x squared plus 1 to the 6th power. If you want to go ahead and simplify the coefficients out front, you can do that, or you could leave it as 1/8 times 1/6. The online homework is smart enough to recognize if you type 1/8 times 1/6, it knows that that's the same thing as 1/48. But you do have to substitute back in for your u. And you do need to remember the plus c at the end. Okay, and there are other forms for this answer. As I mentioned at the beginning, if you really wanted to multiply this all out and then just do basic antiderivatives for each term, you could do that and it would be equivalent to this, but this is the simpler form of the answer and the simpler way to do this problem.